Welcome back, folks. We're going to take a look at some circuit theorems, some more circuit theorems. We've moved on from superposition, and we have two more theorems that I want to talk about, and they're pretty important. In some ways, I think these are the most important theorems we're going to study, and maybe I'm just saying that because I want them to really stick with you. We're going to get lost in figuring out how to apply these theorems. We're going to get so lost in figuring out how to apply these theorems that you're going to forget why it's important. So I wanted to do a video to just talk about what we use these theorems for and why they're important, because they're very important. They might not feel that way. You're going to get so down in the details of figuring out how to find values around these theorems that you're going to lose the big picture. I'm going to try to not let you lose the big picture, because I think it's just as important as the details. In some ways, I think it's more important than the details of figuring out the individual values. Okay, these two theorems let us take large complex circuits, break them into tinier subcircuits, if you will, and then analyze those smaller subcircuits. Okay, so we really want to figure out how tiny chunks of a circuit operate when you start to connect them to each other. And there's a great way to do this. First person to figure this out was a man named Thevenin. He was a French telegraph operator. There's a little, I geek out on the history a little bit. Every time he took his telegraph key, which is a little thing, that thing, and he hooked it up to a different transmission line, he had to reanalyze the entire circuit, okay, because the transmission line was different. And if you've spent any time around engineers, you know that we don't like to do the same job twice. I sure don't. And he figured out, because he didn't want to keep analyzing that telegraph key over and over again, he figured out that the fixed part of the circuit, that's the telegraph key, could be represented by a voltage supply and a series resistance. And later on, we're going to talk about impedances. But it's a voltage supply with a series resistance. So rather than all of the complexity of that telegraph key transmitter, it could just be a voltage supply and a resistance, and we could go from there, right? So it greatly simplified the analysis. Doesn't just apply to telegraph keys, otherwise we wouldn't still be talking about it. I found his original paper. It's half a page long. So when you ask me how many pages do I need to write for this essay, not that we write many essays in this class, I always think about the fact that this guy published a half a page paper, and I'm still teaching it to you over 100 years later. So it's a pretty important thing, right? It's not just limited to telegraph keys. The bench supplies, I want you to think of a handful of things. The bench supplies that we use in lab, every time we hook up a circuit, we don't think of them as having all of the internal circuitry. We think of it as being a voltage supply or a current supply. You turn it on, you hook it up, you set the output, and you go on your way. We can think of that bench supply as being a voltage supply with a series resistance. That's the fixed part of the circuit. And then what we call the load, the thing that changes and we connect to the fixed part, is whatever circuit you're building as a prototype. That's the bench supply. The supply itself won't change, the circuit does that you connect to it. The wall outlet, we don't think about the power plant and the distribution grid and all of the complexities that come from generating power, getting it all the way to your wall so you can just plug something in. We can think of that wall outlet as a voltage supply and a series resistance. It's a pretty powerful thing. It takes all of that complexity out, and we can just start to do analysis on very simple things. Okay? Microcontrollers, and I have a picture of that one. If we're going to hook up something to the output of the microcontroller, then we can think of the microcontroller itself as a voltage supply and a series resistance. Okay? The thing you're connecting to the microcontroller, that's the part of the circuit that changes. That's the load. If you're connecting something to the input of the microcontroller, well, we can still think of the microcontroller, the input of the microcontroller, as a voltage supply and a series resistance. It might be a different one depending on whether it's the input or the output of the circuit, but we can simplify it. So whatever else we connect to it, we can say, how is that going to operate when it's connected to this circuit? Okay, we would do that with a microcontroller if it was a sensor. So if you're instrumenting anything, if you're trying to take measurements, and you're connecting a sensor to something that's supposed to read that sensor, you need to think of that sensor as a voltage supply, some of the time, I'll tell you why in a second, and a series resistance. Okay, it's a very, very powerful thing that we can do with Thevenin's theorem. Okay, years later, there was a guy named Norton, and Norton, we finally got an American. It was this, we had Holy Romans, we had Prussians, we've had I think who else? We had Brits in there as well. It took this long in the semester to get the first American studying this stuff. That's just, if you want to go learn the history of technology and how it was being studied, it might be an interesting one. There's a guy named Norton. He was working for Bell Labs, and he actually was born in Maine, so he's not just American. He's from New England. He was working for Bell Labs, and he was working with sensors that put out their measurements using currents. He got really tired of converting these currents to voltages to be used with Thevenin's theorem. And Norton figured out, hey, if I can do that with a voltage supply and a series resistance, that's Thevenin, Norton said, I can do it with a current supply and a parallel resistance. Okay, so there's a bit of a change there. So we're going to spend the bulk of this section finding Thevenin voltages and resistances and Norton currents and Norton resistances. The use of these theorems sometimes is easier than that. We don't always have to go find these values. Sometimes we can go find them in a data sheet. It's unlikely that the data sheet's going to say this is the Thevenin voltage and this is the Norton current. It's probably not going to say that. But if you know what you're looking for, you can often find it in the data sheet. We're going to do so much work trying to find these values that you're going to lose sight of the fact that we're using this to simplify a circuit that isn't going to change and connect it to something that is going to change. That's the real power here. Okay, so we might, there's my notes. Oh, I totally ruined that. I was reading off my screen. Could you tell? Anyhow, this is what I wanted to show you. We're going to spend so much time finding the values that we're going to lose sight of what we're doing. So this is one of the examples that we talked about. Maybe we have this voltage divider on the right. I should have done this left to right since it's an input. But we want to measure the voltage here, and we want the microcontroller to be able to measure that voltage. Okay, so we would do a couple things. Maybe this one's variable. Let's make that one variable. Okay, it's behind me. So I drew a line through it, and that tells me it's a variable resistance. And maybe it varies with the turn of a potentiometer. That would be a way to get some input from the user. Maybe it varies with temperature. 100K is a little high for that, but you know, it could be a sensor that the resistance varies with some value, and we need to get that voltage into the microcontroller. The way we would do that is, well, we connect the ground. Sorry for the union wiring. It might be better if I just drop out altogether. Bye-bye. And we connect the analog input here to the node where we want to measure the output. Okay. Now, we don't know what's going on in the microcontroller. The company isn't going to magically give you the schematic for the microcontroller. And even if they did, you really don't want to analyze this whole microcontroller circuit just so you can figure out what the voltage is here. Instead, what you're likely to do is dig through the data sheet, because what the company will give you is the something that's equivalent to the Thevenin voltage and something that's equivalent to the Thevenin resistance. And we can think of that input as having some voltage supply internal to the microcontroller and some resistance in series. I'm going to draw it down here because I got to avoid that label. And we can say this is R Thevenin and this is V Thevenin. Okay, now we have a circuit that we can actually analyze instead of having to analyze this whole complex microcontroller. That's the real power that both Thevenin's and Norton's theorems bring to the table. Okay, so scrolling down a little bit, these are the first drawings of a Thevenin equivalent on the left, which I clearly had a nice CAD drawing for out of my notes, and I don't have the Norton section written yet, so it's all coming from there. So you have a hand-drawn Norton equivalent. Okay, inside the yellow dotted lines, we have the fixed portion. Let me actually write that. Okay, so this is the fixed circuit. Sure, we'll go with white. I wanted yellow. Tough luck, you get white. Okay, this is the fixed portion of the circuit. So for Thevenin, this was his telegraph key. I've used it to represent sensors. I've used it to represent power supplies, all sorts of things. Sorry for the phone. Okay, for Norton, this was his sensor that was putting out a current. For Thevenin, this was the telegraph line that he was connecting his telegraph key to. For Norton, he was probably reading this sensor somehow. I'm not sure exactly what he was connecting it to, but that would be the load over here. Okay, here we go. Thevenin is a voltage supply with a series resistance, and then because we can kind of do everything backwards with these theorems, a Norton equivalent is a current supply with a parallel resistance. Okay, so this is voltage and series, and this is current and parallel. Okay, where do we go from here? If I give you these two theorems all in one shot, the playlist will be really long, the assignment will be really long, you'll riot, I'll quit, nobody learns anything. It's no good. We can't do that. So even though you're watching this one at the beginning of the Thevenin section, which is probably going to be the longer of the two, we're going to break this into two. Okay, so we're going to learn Thevenin's equivalent, and then we're going to take what we learned from Thevenin, and then we're going to bring it over and we're going to talk about Norton, which is going to be a lot quicker because we'll be smarter by then, right? Well, we'll be better educated, hopefully. Smarter we can argue about. Keep working at it. Keep pressing the play button there. Answer the questions in WebWork as best you can, and hopefully they're simple enough. I'm trying to make them just simple touch points here. You're going to have a couple on this video. All right, so how do we take a circuit and find the Thevenin equivalent? That's what's coming up next. Stay tuned. Good luck.